Okay guys, welcome to today's lesson in statics. Today we're covering number 61 from chapter 3. So problem 61 says, a sign erected on uneven ground is guided by cables EF and EG. If the force exerted by cable EF is 46 pounds, determine the moment of that force about the line joining points A and D. So a little explanation of what we're solving for. If you look on the free body diagram and also in the diagram itself, we're going to have a moment about A, which is being caused by the tension force going from E to F. We want to figure out what component of that moment acts on the axis A to D. So I'll draw this out in the diagram. We have our vector going from A to D. We'll have to find the unit vector for that. We have a position vector going from A to E. And we're going to find the tension going from E to F. So remove this for now and bring them back up as we find them, each one. So we're going to write our equation out for our moment. Our moment component about axis A to D is equal to the unit vector going from A to D, dotted, doing the dot product, with the moment acting at point A. Now we can expand the moment force, the moment component, we can expand this into a cross product going from point A to E, where the tension is being applied, and this is crossed with the tension force, the tension vector, going from point E to point F. So we have our setup right here for our three main values we need to find in order to compute the moment about axis AD due to the tension at point E going to F. So our first component we'll find the unit vector going from A to D. We know our equation for the unit vector going from A to D is equal to the position vector from A to D divided by the distance from A to D, the magnitude of the position vector. So first we'll go ahead and find the position vector going from A to D. Looking at the diagram, it appears we have an X component coming out on the positive X axis of 48 inches. So it'll be 48 I hat. It appears that the D side leg, the D leg of the wooden post appears to go down to the ground, or down on the uneven ground, 12 inches. So we'll subtract 12 J hat. And finally, we have the K hat value. We're coming out in the Z axis a positive distance of 36 inches, so plus 36 K hat. So you already have our position vector from A to D. Now to compute the distance, we'll simply do the square root of the square of each component added together. So the square root of 48 squared plus, in parentheses, negative 12 squared plus 36 squared. We determine our distance from A to D. We can plug into the calculator. So we have, one second, we have our calculator out. We have 48 squared plus, in parentheses, negative 12 squared. Make sure we put the square outside the parentheses. And then plus 36 squared. So we square root this number. We determine our distance from A to D is approximately 61.2 inches. So we have our unit vector from A to D. We determine that by dividing each one component for the position vector by the distance from A to D. Good. So now when we go ahead and divide this out, we have 48 over 61.2 I hat minus 12 over 61.2 J hat plus 36 over 61.2 in the K hat in the Z axis direction. So when we divide all these values out, we'll figure out our unit vector from A to D. And I'm going to do a trick. I'm going to store this answer as X, and then just divide each value by X in the calculator. So 48 divided by X, we have 0.784, and I'll go another digit, 5 I hat, minus, now we have 12 divided by the number, so negative 12 divided by our number stored as X, we have, so minus 0.196 j hat. And finally, in the k hat direction, we have 36 divided by the 61 number, 0.2, and we get 0.588. So plus 0.588 in the positive k hat direction. So we have our position vector, our unit vector going from A to D. We have this. We're going to check this off. Good. So we have this component right here. Good to know. Put a little check. We have that. Now to find the position vector going from A to E, we first need to notice on the diagram that point E is given on the diagonal, on the direction of the sign. We need to break this into its x component in the x-axis and z component in the z-axis. So I've gone ahead and drawn this diagram down here. If you'll notice, we have the 45, looking at this from the top, looking at the sign from the top, we have our 45 position, and we have our x and our z component trying to find at point E. We have 36 given going from B to C, however, and 48 given from going on the z direction as well, going in the x direction close to the z-axis. So B to E over B to C, notice we have 45 given from B to E. We can calculate what B to C is knowing these two components. Notice I have the 36 dimension right here in the Z, and we have the 48 right here in the X. Okay, so there's no Y distance along the top of the sign, so Y will be 0. So we simply have this is equal to the square root of 48 squared plus 0 squared in the Y plus 36 squared in the Z. So we get 45. We type this out. We have 48 squared plus 36 squared. Square root of this number is going to give us 60. So we have 45 over 60. This will reduce down to 3/4. So that tells us in the x direction that B to E will be 3/4 in the x component. In the z direction, B to E will be 3/4 of B to C. So this tells us now that BE equals 3/4. B to E is equal to 3/4 of B to C. Now we can compute what the x and z component is from B to E. So simply say we'll have B to E in the x is equal to 3/4 times 48, which is going to be 36, and B to E in the z will also be 3/4 times the 36 dimension. The 36 dimension is not the same. It's coming from this distance going out on the z-axis from the x-axis to C. It's 36. 3/4 of that would be 27 inches. So now we have our components, at least our x and our z component, going from B to E. This will help us compute our position vector going from A to E because B is directly on the top of A. So now we need our position vector going from R from A to E, and that will be this x dimension, 36 in the x, I hat. Now we have to look in the y dimension, going from point A to point E, you're going up vertically this dimension, 96 inches, so plus 96 in the j hat component. And finally, we're coming out on the on the z, 3/4 of this. This would be 27 inches. So we have this value right here, plus 27 in the k hat direction. So now we have our position vector going from A to E. So we have 2 of our 3 values we need, 3 vectors we need, in order to compute this moment about A to D, axis A to D. So finally we can write the equation for tension going from E to F. We know the tension force from E to F will simply be the tension scalar value we have right here, 46 pounds, multiplied by the position vector going from E to F, and then divided by the distance from E to F. So, next we need to determine what is the position vector going from E to F. So our R position vector going from E to F, we look on the diagram, we know we have to go from E to F. We're starting at position of 36, 96, and 27. So simply take the coordinates for point F, the new point F coordinates subtracted from point E's coordinates in order to figure out what the position vector from E to F is. So point F, it appears to have come out of the page in the x-axis direction by 21 inches. So it would be 21 minus the position already of point E, which we know is 36 I hat, plus we're going down a distance of 96 inches down to the ground floor, but then point F is also a distance of 14 inches down. So we negative 96 and then minus 14. Actually, we want to stay consistent with point F's coordinates first and subtracting point E's. We would do minus 14 minus 96 in the j hat direction. And finally, in the k hat, point E already has a position of 27 away from the x-axis in the z direction. Point F, it appears to have come out has come out 57 inches from the axis. So we'd have 57 minus 27. Okay, so we can compute the position vector by simply doing these subtractions. So it would be 21 minus 36. Go to our calculator. Okay, so we have 21 minus 36. Okay. Yeah, it should be negative 15. So it'll be negative 15. We have negative 14 minus 96, which is going to be, so in I hat direction, be negative 110 in the j hat direction. And finally, we have 57 minus 27, which will simply be positive 30 in the k hat direction. Good. So now we can compute the distance from E to F by doing our distance formula, the magnitude formula. Distance from E to F is going to be the square root of each component we just determined, squared and added together, square root of that. So it would be negative 15 in parentheses squared plus negative 110 in parentheses squared plus 30 squared. So we're going to say in parentheses negative 15 squared plus in parentheses negative 110 squared. Oops, grab the 0. Okay. Okay, and then finally plus 30 squared. So square root this answer. Oops, no, square root this answer. We get 115 for the distance from E to F. Good. Now we have everything we need to go back and compute the tension vector from E to F. So we have the tension value, which is given to a scalar value of 46 pounds. We have the distance, 115. And finally we have the vector. We have the vector components of negative 15 I hat minus 110 j hat plus 30 in the k hat direction. So we're going to say 46 divided by 115. This is equal to 0.4 multiplied by negative 15 times negative 15. So multiply 0.4 times each one of these components. So 0.4 times negative 15 to give us negative 6 in the I hat component. We're going to have a negative value in the j hat, so we have 0.4 times 110, which would give us negative 44 in the j hat component. And finally, we have 0.4 multiplied by 30, which would give us positive 12 in the k hat component. So we have our tension E to F. So we have all three components we need to calculate this moment, and then also dot it with this component to get the moment about axis AD. Okay, so finally we can set up our matrix, or determine for our matrix. We have moment about axis AD is equal to the unit vector from A to D dotted with position vector from A to E, R from A to E, crossed with tension vector going from cable E, point E to point F along the cable. Alright, so when we set this up, we will have, I'll draw this out symbolically, we would have the I component for the unit vector, the components of the position A to E, and we have the tension vector in the bottom row. So, looking at the unit vector A to D, we have right here, we have 0.7845 I hat. We have negative 0.196. Make this a 0. Negative 0.196. And finally, we have positive 0.588 for our unit vector going from A to D. Now, position vector going from A to E, we have right here 36 I hat, positive 96 in the J direction, in the Y-axis direction, and then positive 27 in the Z-axis. Finally, we have our tension vector, which is negative 6, negative 44, and 12. Now, to solve this determinant, we could write out the columns, repeat the columns, I hat, J hat columns, I and J columns, and then do our typical diagonal method, adding and then subtracting the products. What we can do, since this is a scalar value, there's no moment here, there's no vector here, I should say, we can actually do this by using the determinant of the calculator. So we use our calculator function and determine what the moment about axis A to D is that way. So I'm going to go to my matrix, my calculator. We're going to go over to edit. Do the first one, it's already 3 by 3. We need to override these values. So we have 0.7845. We have negative 0.196. We have 0.588. We have 36, 96. The calculator appears not to be catching everything, so 36, so 96. Go back over and fix this as 36. Okay, 96, 27, negative 6, negative 44, and finally 12. Now we'll do second quit, get out of our matrix, go back to matrix, second matrix, go over to math, determinant, and one last time we'll go to second matrix and select matrix A. And this tells us the moment component along axis A to D is 1359, 1,359 approximately. We'll round this down. This is in units of pound, force, inches, or inch pounds. Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.